This will be a presentation on Brownian Motion by Robert Snyder, or as Dr. Lau likes to call me, Thanos. So I wanted to do a presentation on Brownian Motion because of how much it impacted the world, even though at the time when it was discovered, people didn't think much of it. Robert Brown, the guy that made the discovery, as you'll come to learn more about, just kind of brushed it off, and it really didn't have much of an impact for a few years until they started realizing how much it actually is affected in terms of atoms. So I'm going to go into that a little more, and we're going to cover some of the interesting aspects of it and a little bit of the math, but overall we're going to stay away from most of the math and just kind of do a broad overview of what Brownian motion was and is and how much it has affected physics as we know it today.
A little over 200 years ago, atoms were just a thought to some people, but there was no real proof in anything. In today's world, we know of atoms and learn about them from a young age, and think of them as commonplace, and we really don't have a second thought about them when we learn about them in school. So the question is, when and how did atoms become such an accepted fact in science? So for the next 20 minutes or so, we will first cover the history of Brownian motion. After this, we'll move on to the impact it has had on shaping science as we know it to be today, and the people that were responsible for making major contributions. One of the most well-known being Einstein and his theory. We will then just touch on Chomsky and some of his work. I then would like to talk about random walks before lastly touching on how this can be applied to the galaxy, very quickly before moving into the conclusion, where we will recap on some of the major points of the presentation and the effect that the discovery of Brownian motion has had on the world. Lastly, I will show my references that were used while I did my research on this presentation. As you heard, I am not very good with pronouncing names, so please forgive me as I butcher names throughout this presentation. Okay, so first let's look at what Brownian motion is and how it came to be. Brownian motion is defined as random motion of particles suspended in a fluid, whether it be a liquid or a gas, resulting from their collision with the fast-moving molecules in the fluid. This phenomenon was first discovered by a botanist by the name of Robert Brown in 1827. He was looking through a microscope at pollen, which is approximately 1 micrometer in diameter, when he noticed that the pollen was moving randomly while it was immersed in water. As you can see in the images, the simulation on the left has much more movement of the particles that are being tracked. This is because of the size. Because all the particles in the image are in the same size, in other words, the little ones that are being tracked along with all the random particles moving, they are all moving much more drastically. When on the right, the pollen does not move nearly as much. This is because of the size of the pollen in reference to the particles hitting it. The pollen is much more massive compared to the little particles that are actually bombarding them with movement. So this brings us on to the next point, which gives us John Dalton. So if you think about it, if you were to see these pollen molecules moving around randomly in a fluid, you would have no idea what was going on. However, going back just 19 years before Robert Brown initially made the discovery of Brownian motion, in 1808, John Dalton, who was an English chemist, physicist, and meteorologist, proposed the atomic theory. This is a theory that consists of the most important of all of Dalton's investigations. In a nutshell, the 5 main points of Dalton's theory eventually developed into the following. Number 1. Elements are made of an extremely small particle called atoms. Number 2. Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Number 3. Atoms cannot be subdivided, created, or destroyed. Number 4. Atoms of different elements combine in simple whole number ratios to form chemical compounds. And number 5. In chemical reactions, atoms are combined, separated, or rearranged. This brings us to Albert Einstein, who in 1905 had a breakthrough paper called on the movement of small particles suspended in a stationary liquid demanded by molecular kinetic theory of heat, which was one of the 4 groundbreaking papers that he published that year. This paper was the first statistical physics analysis of Brownian motion, which proved the reality of molecules is not only in the water itself, but all around us. In 1908, John Perrin was able to confirm the existence of molecules experimentally that proved Einstein's explanation of Brownian motion to be correct. To do this, Perrin was able to map the movement of 3 particles by determining the area in which the particles could travel to find the distance and then marking their location of 3 particles every 30 seconds. These mapped particles showed just how truly random the movement could be. You can see these 3 random motions that he mapped in the same paper on the right. To cover Einstein's theory, it would be easy to go in depth and take well over an hour or 2. So here, we will just have an extremely brief overview and just give a flavor of what it's all about. There are 2 main parts of Einstein's theory. The first part consists in the formulation of a diffusion equation for Brownian particles, and the second part relates the diffusion coefficient to measurable physical quantities. In this way, he was able to determine the size of atoms and how many atoms there are in a mole. The first part of Einstein's argument was to determine how far a Brownian particle travels in each time interval. Up until this point, what was known about classical mechanics, there was no way to determine the distance because of the enormous number of bombardments of a Brownian particle, which would typically undergo approximately 10 to the 14th collisions per second. This was the reason Einstein was led to consider the collective motion of a Brownian particle. The second part of Einstein's theory relates the diffusion constant to physically measurable quantities, like how much a particle moves in each time interval. This is what brought about the experimental determination of Avogadro's number, and this is how he found the size of the molecules. The type of dynamical equilibrium proposed by Einstein was not new. It had been pointed out previously by J.J. Thomson at Yale University in May 1903. This is a very general overview of Einstein's theory without getting into the math of it all. There are lots of sources and papers that cover this, to include Einstein's very own called The Investigation on the Theory of Brownian Movement. So I do want to mention Smolowski's model. So as you can see, I can't really pronounce his name, so from here on, I'm going to call him Ski. He was able to start with the same premise as Einstein, and was able to determine that the same probability distribution for a Brownian particle. However, he relates the particle mass m moving at velocity u, he gets a fraction of 27 over 64 for his mean square displacement. This was commented on by German theoretical physicist Arnold Sommerfeld, and I quote, the numerical coefficient of Einstein, which differs from Ski by 27 over 64, can only be put in doubt. Ski attempted to answer the question of why a Brownian particle should be displaced, and he did a good job in general. However, as a result of the simplicity of his one-dimensional model, it can only be used to quantitatively describe Brownian motion, because for a real particle undergoing Brownian motion in a fluid, many of the assumptions that Ski made out do not apply. For example, his assumption that the number of particles hitting from the left is equal to the number of particles hitting from the right. However, if a Brownian particle is already in motion, this will fall apart. The last person I want to highlight in this whole history is Norbert Wiener. He took great interest in the mathematical theory of the Brownian motion. He essentially minimized the Brownian motion to one dimension and created a random walk. This is now known as the Wiener process, which can be characterized by the 4 properties listed here. I will not read through them word for word, but what they generally break down to and mean is that all particles start at the same location at time zero. The second thing that we must consider is that for every future step is independent and it can go anywhere, so long as it starts at the location from where it just left off. The Gaussian increment is to say that after a large number of trials, we would have a normal distribution, which I will go over shortly. And finally, we know that our path must be continuous. In other words, we can't just pick up and start wherever we wish. We must make these paths without any breaks. Okay, so now I want to demonstrate what some of these random paths mean and how they affect the whole process of Brownian motion. The image you see is from an online random walk simulation. You are able to choose the number of particles, the number of steps, and then decide if you want to take a one or two-dimensional walk, or if you would like to see a variance or distribution. What you are seeing here is that I chose to start with a one-dimensional walk. I used one particle to show how this works. As you see, it is very sporadic movement. Now I chose to do 1,000 steps, although you can choose to do anywhere from 10 to 100,000 steps. The reason for choosing 1,000 is so that I did not overload the processing of these steps, which I have done a few times while looking into different graphs. Now I ran this process 2 more times, and you can see that the paths are truly and indeed random. I then moved on to 200 particles. Again, this keeps the program processing at a reasonable speed because it takes 1,000 steps for every particle, and with 200 particles on the computer must run for a total of 200,000 values, and then plot them, which as you can see gets very messy very quickly. But you also see how random these paths can become, even though they overlay on each other. So this process can also be moved to 2 dimensions. Very similar, we can see that the paths are random for each individual particle. And if you were to graph a total of 200 particles taking 1,000 steps each time, this is the type of movement we can expect. As you see, they all stay reasonably on top of each other, but you do have a few outliers, like the purple one that went straight up and that blue one that went more left and down. But even then, we still see that most of the paths are in a general central area. This brings us to the distribution of the movement. The way that the distribution works, we start here at time equals 0. As you see, we have a line going straight up and down. Now this represents all the particles at one point when the time is 0. In other words, before we start the distribution. We'll consider each step one increment of time. In other words, if I say time of 5, then that would mean that each particle has taken 5 steps of their journey. So, as you see, at time 0, we have a straight line, and at time 5, the particles have started to distribute. You can also see that there's a white line that traces the outside of the red, and this is called a normal distribution. Now, as you see, as the time goes on to 50, our curve starts to move out a little wider, and our particles are a little more sporadic. Some are still in the middle, and some have now stretched out a little farther. If you also notice on the y-axis, we've gone from 200 down to 40. So this graph actually zooms in quite a bit. So although it looks higher, it's actually much lower. Then we go to time 300, and our graph zooms in even more, and our spread is even wider. As you see, our distribution is also getting flatter and flatter. Finally, if we go to time equals 1,000, if you remember from earlier, this is when I decided that each particle would go 1,000 steps. So here you're seeing the distribution of all 200 particles at time equals 1000. Also, you see that at time 0, we went from a straight line to time 1000, where all particles are completely spread out. At 0, you still see that there are still a few particles that are back there. So in other words, those have gone around, and after 1000 steps, they've gone back to the very original starting point. Whereas most of the particles have spread out, which is expected, and you see the normal distribution curve. Although it's a rough fit, you see that it does slowly get wider and wider. The only thing we can see here, because I restricted myself to time equals 1000, you notice that the time is not going to go into infinity. If the time continued to infinity, we could expect this graph to get, or the normal curve, to get lower and lower and more spread out. Now again, the only reason I didn't go farther was computer processing, and I didn't want to overload the online simulation. This brings me to the last topic I want to briefly talk about. That is, in interstellar dynamics, a massive body such as a star or black hole can experience Brownian motion as it responds to gravitational forces from surrounding stars. To do this, they relate the energy of the large star or black hole, which we would consider to be the Brownian particle, to the energies of the other stars around it. So the massive object causes nearby stars to move faster than they otherwise would, and vice versa, increasing the velocity of both the stars around it and its own velocity. For example, the Brownian velocity of a supermassive black hole at the center of the Milky Way galaxy is predicted to be less than 1 kilometer per second. So this brings us to the end, and I just want to do a quick recap of what all this means to us. Just over 200 years ago, we had no idea about anything with the atoms. There was only knowledge of classical mechanics and what we would expect with gravity and all the simple equations. Once Robert Brown discovered these, Brownian motion, is when we really started to take a turn for the molecular world. So to recap, we first covered the history of Brownian motion and how it was discovered by Robert Brown with pollen under a microscope. We then looked at John Dalton, who proposed the reality of atoms in 1808, before first touching on Einstein and Perrin, who really brought Brownian motion to a new level, in both theory from Einstein with his math and experiment when Perrin was able to map the molecules. This brought us on to Einstein's theory, which had the two main parts, with the first being the formulation of a diffusion equation for Brownian particles, and the second was when relating the diffusion coefficient to measurable physical quantities. We then finally moved on to Wiener and his impact with the random walks, which took us into what a random walk is, and we showed that off in 1 and 2 dimensions. And then we talked about the particle displacements over time and how the normal curve goes from a nice distribution to flattening out as time goes on to infinity. Lastly, we touched on the stars and the motion within galaxies, and how Brownian motion can be looked at on such a large scale. So the last thing I'm going to cover, of course, is the references. I won't be on this slide for very long, so if you wish, you can pause the video and take down some of these sources that I've used if you want to learn more about the history and impact of Brownian motion. I really appreciate you taking the time to listen to my presentation.